Group Relative Policy Optimization, or GRPO, is the technique used in the much talked about DeepSeek or1 reasoning model. I had a hunch that maybe instead of using this technique, you could get similar results with traditional supervised fine-tuning. And I've created a study where I run through both techniques and a third, trying to train a small model to improve on mathematical reasoning. Now, this is the third part of a sequence of videos, and I'm going to focus in this one on GRPO and comparing the results with SFT. If you want to understand the details of how I ran the baseline methods of SFT, you can check out the first video. And if you want an intuitive understanding of how GRPO works, you can check out the second video. Today, I'm going to describe the study again. I'll give a high-level overview, and I'll share then the results. I'm going to walk through in detail how to run group relative policy optimization and talk about some optimizations that helped me to converge the performance faster. And I'll show you the detailed run logs and walk through those as well. Then I want to talk about the similarity in all of these methods, SFT and GRPO, and help appreciate some of the nuanced differences between them. Last of all, I'll talk about how you can do reinforcement learning, either via GRPO or with SFT and rejection sampling. And I'll talk about how you might think about whether you should do GRPO or whether you should do supervised fine-tuning. This study is all about improving the maths performance of a very small model, Llama 3.18b, and I do that using a grade school maths dataset with about 8,000 samples. It's actually GSM8K. The training set's got about 7,000 rows, and the test set, which I use for evaluation and I don't expose during any fine-tuning, has got about 1,000 rows. You can find the model that I'm training on Hugging Face. It's the Llama 3.18b, rather 1b model. Did I say 8b? It should be 1b, and it's actually 3.2. And I use it from Unslot's organization just because that's not gated and doesn't require you to add a token in order to download it. The data set, I'll just show you that quickly here. You can find it if you look at GSM8K. It's actually an OpenAI data set and has closer to 9K samples, but it's called GSM8K. The split of training data is 7.5, and for test, it's almost 3,500 rows. So my goal is to improve performance using 3 different techniques, actually. It's not just SFT versus GRPO. I also compare using sampling and odds ratio preference optimization. And the reason I do that is because I see a lot of analogy, a close analogy between odds ratio preference optimization, a little older technique, it's only 2024, versus GRPO, which I guess actually is 2024 as well because it came out in a maths paper from DeepSeek during the year. But understanding ORPO helps a bit to understand GRPO and vice versa. So here's how I approach things for each of the methods. I've got a slide on each of the methods here. Let me describe each of these slides, how I do the training, and then I'll move to the code, and I'll give a very quick overview of what I did in the previous video before describing GRPO. So the first method, supervised fine-tuning, and it's not pure supervised fine-tuning, I'm combining it with what's called rejection sampling. I start by using the instruct model, that's just the base model here, Llama 3.21b, to generate 8 answers per training question. So that means if I've got 7,000 training questions, I generate 56,000 questions. Then I check the correctness of those, and that is a nuanced manner. I actually use exact match, but I use a fallback then of a powerful language model to check in case the exact match failed. So I keep the correct answers, and I use those answers then. It turns out I've got about 14,000 correct answers after doing that. I use the correct answers to do supervised fine-tuning for 1 epoch at constant learning rate. And then I reevaluate performance and it gets better. I'll talk about how it gets better. And then you can do this for iterative rounds. So you can use that better model to regenerate answers, another 56,000 answers, keep the correct answers and go back and do SFT again. Or alternatively, I'm adding quite a bit of nuance here. You could take that better data set and just use it to train the base model. So you can kind of bring the model with you and keep improving on the model you've already fine-tuned, or you can just go back and train the original model. And interestingly, it's not entirely clear. You need to run a lot of data in order to see differences between those 2 approaches. Sorry, that's getting a bit sidetracked. Let's get back and talk a bit about the second method, which is ORPO. So I've talked about supervised fine-tuning, and now I want to talk about odds ratio, preference optimization. This is pretty similar to what I do for supervised fine-tuning. I again generate those 56,000 questions, but now I use those answers, which are correct. There's about 14,000 correct, and then the rest, the balance, I guess 42,000 incorrect. I use those to create pairs. So I only allow each correct answer to be used once, and I pick a random incorrect answer for that same question. And I create these correct, incorrect pairs, which are, what's the word? Chosen. Chosen is the word used for the better one, and rejected is the word used for the lesser quality one. So I take these chosen, rejected pairs, and I use those to run a backward pass using ORPO. Now, ORPO, it uses pairs instead of just using the correct answers. And so it's a bit like supervised fine-tuning, but whereas supervised fine-tuning will only try to increase the probability of the good answers, which mathematically has to kind of evenly reduce the chances of all the other bad answers, ORPO does something a bit more nuanced, which is it makes the answers more likely to be good and less likely to be bad. So you can think of supervised fine-tuning as just making answers more good, or making the answer more likely to be good, whereas ORPO is kind of a bit more surgical. It's both improving the chances of a good answer, but it's also reducing the chances of a bad answer. Now, as I said, because mathematically, if you increase the chances of anything, for every probability to add to 1, you have to mathematically decrease the chances of every other outcome. So you are reducing the chances of bad answers with SFT, but the exact shape with which you're reducing those chances is different. It's not as surgical. Okay, so this is ORPO. And the third method then is group relative policy optimization, which is the DeepSeek method. And here you'll see again a lot of similarity inside the library, and it's all wrapped into a library, so you don't see this as clearly, but this is what's happening. You use the model to generate K answers per training question. I'm using 8. And when you have those, you don't actually throw out any examples. You keep all of them, and you backpropagate using group relative policy optimization. Now, what does that mean? It means that if you take this group of 8 answers, GRPO is basically going to try and move the model towards the good answers there and away from the bad answers. It's like a group version of ORPO in some senses, because ORPO has a good answer and a bad answer, and it tries to move you towards the good one, whereas GRPO has got kind of a pool of answers of different qualities, and it tries to move you towards the good ones and away from the bad ones. So that's why I've written here, ORPO uses pairs to shift the odds towards good away from bad. GRPO uses groups to shift the odds towards good answers in that group. Now, GRPO also has 2 other things that are a bit more nuanced. One is it has a KL divergence term. That means GRPO will penalize the model if it moves away from what its original guess would have been by too much. And the reason for this is it tries to stabilize the training. You don't want a model to move too far just because of a given group. You want to constrain it close enough to its home base. This is what KL divergence does. And GRPO also has got clipping, so it will limit the size of moves of the model. So it will limit how far it's able to move. Now, you always, in some sense, have got clipping, even with SFT, because you're going to choose your learning rate, which affects the step size. So it's not like you don't have any clipping in SFT. It's just you don't have explicit clipping added on in addition to the learning rate lever that you have. Something else I'll note is that to avoid divergence in SFT, a common approach is to blend in some of the original pre-training data. So even if I'm generating correct answers and I want to train on those, I can also blend in some original data, maybe that covers even unrelated topics. And by blending it in, it kind of pulls the model back to its base, or at least avoids it from diverging too far from where its base of knowledge was. So there are different ways of kind of achieving similar effects. And you can draw an analogy kind of between doing KL divergence to pull it back, which is based on keeping the same shaped probability distribution, but you can also kind of do that by just including some of the original data in the fine-tuning data set to keep it close to home. Okay, so I've described the 3 methods. supervised fine-tuning, rejection sampling with odds ratios, and then GRPO. Let's now look at how I implement that in code. And the code for this, as for the previous videos, you can check out if you go to trellis.com/advanced fine-tuning. This is a private repo, and it's available for membership purchase or lifetime access purchase. But I will say two things. First of all, if you're just watching this video and you're not in a position to purchase these, hopefully at least you'll get the big ideas, and using Cursor, you should be able to replicate this yourself. And second of all, the script I'm going to use today is going to be heavily based on an unslot script. So you can find a version of GRPO that you can run for yourself. If you go to unslot and GitHub, you can find here a free collab notebook called GRPO or1 reasoning. And you can just click on that and run GRPO for yourself. So that's a way you can run for free if you're interested. Now, I have integrated a lot of this functionality here. I've kind of changed a few things so that it meshes in with my study comparing SFT. But broadly speaking, you'll be able to follow this here for free. So I've git cloned the advanced fine-tuning repo, which contains a wide variety of scripts. It includes also work on retrieval augmented generation, includes distillation methods, data preparation methods. But I'm in the RL branch, RL for reinforcement learning. And I'm looking at the study that I described in the first of this 3 video series. So I'm going to bypass a description of everything I've done in detail for SFT, but I will note a few improvements that I've made since the first video. So when I run supervised fine-tuning, to recap, the process is as follows. I first generate some samples through sampling. So here you can see I'm running a sampling script, sampling batch inference. I'm running it on the base model, untrained, and I'm going to sample 8 times per question. And if I'm running evaluation, I'm going to do that on the test split of about 1,000 samples. If I'm running on the training and I want to generate training data, I would swap this and I would say GSM 8K and do train. And then I would run on the full 7,000 samples like that. So this is how I generate samples. Once I've generated samples, I will take the correct answers and I will do training on those. And once I've trained the model on the correct answers, which is done by running a training script like this one here, train unslot supervised fine-tuning, I'm then able to run inference again and see if I've been able to improve the performance or not. Now, in the first video, to save time, I didn't run my evaluations on a test set of 1,000 samples. I ran it just on 100 samples that I'd filtered out. And this obviously makes it quicker, but I found there was too much variance and it was hard for me to tell if one method was better than the other. So I increased the number of samples every time I evaluate, which meant it's slower now. It takes about 10 minutes to evaluate, maybe 15 minutes. But it means my data is a bit more robust and I see less variance when I run the same command twice. So I ran the tests on the baseline model using a much larger data set. And I just want to share that performance here because this is the baseline figure that we'll see in graphs and that we want to think about when we compare the performance of the fine-tuned models. My base model, without any fine-tuning, is scoring, and this is the correct one to look at, I'll say why. It's scoring just about under 80% in pass at 8 and a majority at 8. If you force it to have 5 or more answers correct out of 8, it's scoring 35%. So this matches what I said earlier, or at least what I showed on the slide with the scoring of the model. Just to recap here on what this means, pass at 8 means I allow it 8 attempts, and if it gets any of one of those 8 correct, it's marked correct. Majority at 8 means it's allowed 8 attempts, but it must get 5 or more, a majority correct, in order for it to be marked as correct overall. And then I run this across the full data set. Now, there's a nuance point I go through in the first video, which is around how you mark these answers correct. They're marked correct by checking for numbers in the answers, doing exact match, and then falling back to an LLM to compare the ground truth with the answer provided as a fallback if the exact match fails. This is important because you can find edge cases, and if you don't handle those edge cases correct, you can sometimes think you're getting improvements, but really it's just because of how you're evaluating. And actually on that point, I evaluate without being strict on format. I just want to know whether the model is getting the answer correct. because sometimes if you fine tune or do GRPO, you think your performance is improving, but really what's happening is you're just formatting it the way that you want your evaluator to see it. And so the model may have been getting the answers correct all the way along. It's just that when you ran the judge or the evaluator, you weren't recording it as correct, even though it was. So this is something to think about. Make sure that you understand how your evaluation is working and that you're measuring what you think you are. I mean, it's generic kind of advice, but important to follow. So here we are with a baseline. When I say without think tags requirement, it means I'm not enforcing the format. If you do enforce the format, it will score lower, 73-24, actually a lot lower in majority 8K. So yeah, the way that you evaluate and whether you include format requirements really affects the performance that you're going to see. Okay, so now we're going to move on and do GRPO or do SFT. I'll move through that very quickly, and then I'll talk about GRPO and go through the script in detail. So I have the baseline performance here. And next, I'm going to move to run some training with SFT and to run some training with ORPO. And to run those trainings, I need to have data available. And the data needs to be generated by basically running some data creation scripts. I haven't shown them here, but I can write out what the data creation scripts would look like. Let's just write them out here. So training data creation scripts. They're included above, but I'll just show them here to be illustrative. So you run the sampling script, you run it on the base model 8 times, and you run it on the training split. And then also you can run it on the eval set. So you want to create a small eval split that you're going to use for training just to inspect that you're not overfitting. And so here you'd run 8 samples, but I would typically run it on the test set. Now, I don't run it on the full test set when I'm doing an eval split, because that will slow down my training if I have to evaluate 1,000 samples during my training. Now, it would be better because it would give you a more representative sense of overfitting or not, but to save time, I just use a much smaller eval split. So this is how I create training data. And then I will set the data up into pairs by looking at the correct answers. This is necessary for ORPO. For SFT, I just take the correct answers. But in practice, the way I do this is I set up the ORPO pairs, and then I just take the correct answers for SFT, and I use the full pairs when I do ORPO. So this is my script to set up the pairs. Now, here's another improvement I've introduced since the first video, which is to look at the lengths. Look at the lengths of the responses. And I can actually maybe run this here. Let's try it. Okay. So I've run a script that helps me to analyze the responses generated. And what it does is just tell me the length of the answers that were generated. And it tells me that if I look at the chosen responses from my training data set that I've created, the maximum length of the correct or chosen responses is 914, and the maximum length of the rejected responses here is 959. Now, the reason I inspect this is because sometimes, especially when you've got a weak base model that's not answering questions correctly, the model can blab on a lot. And this means that the wrong answers can end up being very long. And if you have a lot of long wrong answers in your ORPO pairs, it can result in having gradient norms that are going to be high. Basically, it's adding noise to the process and it's making it harder to train. So a very simple optimization I've made in creating ORPO pairs is I've allowed for setting a maximum length of the rejected responses, and this tends to stabilize then my gradient norm and makes my training more smooth for ORPO. For SFT, because I'm only focused on correct answers, the correct answers tend not to blab on, and so you don't really have instability issues for that reason there. Okay, so I ran then the training on SFT, I ran the training on the ORPO, and once that's done, I can measure the performance of SFT and the ORPO models. And I can do this by enforcing format with what I call think tags, or I can do it not enforcing format, which I think is the right way to look at performance, because you want to see if you're actually improving the model and not just improving the format. So the results we care about are the results when we don't enforce the format, which are here. And you can see that when we do SFT, we're able to get the majority at K at 8 to go up from 35 to 40. So you remember this was 35. And the pass at 8 maybe goes up a tiny bit from 79 to 81. but it's probably not. It's probably within the bounds of error. Whereas when we do ORPO, we get a smaller improvement in the majority at 8, and we actually don't get an improvement in the pass at 8. So as you'll see in the earlier video, and pretty much this matches my results running with smaller data sets for testing as well. Basically, ORPO seems to get some small improvement, but SFT actually tends to be, well, not tends to be, but in this case, it is more robust. So now we've gone through very quickly SFT and ORPO. And the main focus of the video now is looking at GRPO. So let me scroll down and find the GRPO section. There are some ablations I've included here for those who have repo access. You can test out a few other ablations that I've looked at, or at least read through them. So for testing GRPO, and I will look through the script here. In fact, let's do that right away now. So I'm going to go to train onslaught GRPO. And I am going to use the onslaught library because Daniel Han and his team, Daniel and Michael Han, they've put together a script, a library, in fact, that allows you to efficiently run the sampling and then run the backpropagation on the language model. So this is much better than the scripts that were previously available before then that were taking up a lot of memory because you effectively were trying to load a model for doing sampling and load a model to do backpropagation at once. So this is a significant improvement on how to run GRPO. And it works by running VLLM to do the sampling, which also improves the speed. And then it uses transformers and unsloth for doing backpropagation. Now, I should note that I think SGLang is faster for batch inference than VLLM. So you probably have some drawback by using VLLM in terms of speed. And when I do sampling, say sampling with SFT, I use SGLang for doing the sampling, and then I use unsloth for doing the fine tuning at each iteration. But here in GRPO, everything's in one library and VLLM is being used. Okay, so the first thing I'm going to do is set a system. The system prompt is the guidance to the LLM for sampling on how to generate answers. And typically you would give a simple system prompt here, maybe just saying you're a helpful math assistant, and to respond by putting your reasoning within reasoning tags, and then after your reasoning, provide the final numerical answer. But this is actually a big improvement. If you include a one-shot example here, what you'll find is that your GRPO, at least on the formatting reward, it's going to perform much better from the start, so your convergence will be much faster. If you do not include a one-shot example, you're going to have rewards of 0 for quite a bit of time, because you're basically waiting until the model randomly hits the format that you want. Whereas putting in this reasoning example here helps a lot. Now, if you're training a stronger and stronger model, this kind of system message here is probably sufficient, but the one-shot example really helps when you have a smaller model. Now, there's also here an XML chain of thought format. This is basically the regular expression. You can think of it like a regular expression for the answer, and we're expecting the model to answer in this format. And by using this regular expression, we're going to be able to assign a reward to the model as to whether it achieved that exact format or not. Okay, so I wanted to explain those two things, but now it's probably easiest if I go back down and I start at the main function and walk through here. So first thing we do is read in the arguments for the training, which will include how many samples we want to take. Actually, that's hard-coded, I think, in the script, but it will take in the data set and the model. It will load a tokenizer here. It will get the raw data set. The tokenizer is being used for counting tokens, I think. Set up the system prompt. Calculate sequence lengths. So we need to set that, calculate these. So we look at the length of chosen and we look at the length of the prompt so that we can pass that length into the trainer later. We've got the max sequence length, the max prop length. And now we're going to load the model. So we load it with Unsloth's fast language model. Notice that the model and tokenizer are loaded at once with Unsloth versus transformers. We're going to set the max sequence length, set the model name. I'm not going to load in 4-bit. I'm going to keep it in 16 bits. Fast inference means we'll use VLLM. And you do need to set the max lower rank. I think this ends up going into VLLM for when we're doing that inference. So then I just like to print out the model before we start to set up LoRa adapters. So as with the SFT and ORPO, we don't train the base model weights, we only train adapters. These are small plug-ons for some of the key matrices. We plug these onto some of the attention matrices and some of the MLP matrices here. So typically a transformer's got an MLP block and it's got an attention block. Attention is where it looks back at previous tokens. MLP is where it does neural mixing of the current information. So these all correspond to matrix blocks, and we apply small adapters to them that we're going to train. Now I keep the LoRa alpha and the rank the same as in the SFT and the ORPO, just for comparison. And we're going to use gradient checkpointing, and I like to use rescaled LoRa. You can look at my video on LoRa fine-tuning to understand how you think about setting these parameters here. So with that, we're just setting up some output directories before defining the training arguments. We're going to use VLLM. We're going to use a learning rate that you could argue is maybe too big or too small. We'll see in the logs that actually it performs quite well. So I guess I got lucky with that because I just took the learning rate that actually was being used for an 8B model. You could argue that I should have increased it more because with smaller models, you can usually use a higher learning rate. Now, the learning rate schedule was cosine. I don't like cosine usually. I prefer to train at a constant learning rate and then do annealing if needed at the end because it allows you to pick up from somewhere you left off with less problems. The optimizer, we'll use an 8-bit optimizer. Usually in my videos, I avoid 8-bit optimizers because they can converge less fast than the full precision, but I think it's fine and I didn't see too much in terms of convergence issues. What else to highlight here? So I set up my training batch size to 4. If you run out of memory, I'm running on a H100. You can see how I set that up in video 1. If you run out of memory, you have to reduce this. You also might need to reduce the number of samples, but I really don't want to reduce the number of sample generations here because I want it to be comparable with my SFT method where I use 8. So I would be more inclined to reduce the batch size and then increase the gradient accumulation to make the product of grad accumulation and batch size 32, which is my virtual batch size. And that's the number of rows that are contained within a batch between backpropagation steps. So the GPU will actually only forward prop on 4, but it will then accumulate 8 times in order to get a virtual batch size of 32. And I'm going to save every 50 steps. That'll save the model. And I'm hard coding the completion length. You'll see the completion lengths here are quite a bit shorter, so I could have made that a bit shorter, but I wanted to be safe. Now we can set up the GRPO trainer from Hugging Face, and we'll have the model, the tokenizer passed, and this is critical, the reward functions. So each of these reward functions is calculated based on the outputs created from a sample, and the rewards are all added together to create one big reward that's used as the reward that affects the backpropagation. So any rewards you add in here, and we'll talk through each of these, they're going to be added together for the purpose of backpropagation. Then I pass in my training arguments and my training data set, and I run the training. That leaves us to describe how these rewards work. Now, basically, there are 2 rewards that you need, or there are 2 rewards that DeepSeek say are used. One is correctness. Simply you check, is the answer correct? If it's correct, you give it a score. You could say 2 out of 2. If it's incorrect, you give it a 0. The second type of reward is format. Does it have thinking tags with content between them and then the answer afterwards? You could again do a simple format reward where you say 2 points if the format's right and 0 points if it's wrong. Now, the problem if you just have 2 rewards like that, although DeepSeek say that that's maybe enough, and maybe when they say they just use 2 types of reward, they actually have more granular rewards within that. The problem with those very simple 2 rewards I described is that they're what's called sparse. That means the model is getting either 0 information if it gets things wrong, and it only gets any information if it gets something right. So if it gets something half right, it has no idea that it's kind of on the right track. You can imagine trying to train some kind of robot to play basketball, and you just give it a point if it gets it in the hoop, but you give it 0 otherwise. That means it's going to spend a lot of time shooting hoops where it might even bounce off the rim, and it doesn't score. So it gets a reward of 0, and it doesn't even know that was quite a good shot. So you might try to what's called densify that reward by including a reward for hitting the rim or hitting the backboard. Maybe hitting the backboard is a half point, hitting the rim is 3/4, and getting it in within the basket is 1. And so now you can kind of get the model to learn something, or the robot in that case, even if it gets the ball close to the rim, rather than just have no information unless it gets it through the hoop, which is going to be a rare occurrence if you're randomly shooting a basketball. So you want to densify your rewards, and yeah, it's not necessarily easy to densify your rewards. You can densify the format, but that's kind of the least useful because it's easy to get language models to follow format anyway. So actually how this is working is it's got that kind of sparse correctness function. It's a 2 or a 0 based on correctness or not. And all of these, actually all 3 of these here are to do with format. This one here is also to do with format. Basically, there's half a point here if the response has got an integer. There's half a point if it follows the exact regular expression I showed earlier. There's half a point here if it's got the thinking tags in the right order. So it's got open reasoning, close reasoning, then an answer, I think. And then it's got a reward here if it's got the right number of reasoning tags within the answer. So you can see this is kind of densifying the reward a little bit, but really it's more or less getting it right or not. So this is not a very dense reward, and that definitely makes it harder to train. But as I said, it's not easy to come up with ways to densify the reward. You could think about having maybe LLM as a judge that rates the answer from 0 to 1. But of course, if you have LLM as a judge that can rate it from 0 to 1, maybe that LLM could have just generated the reasoning traces in the first place, and you do supervised fine-tuning. So these are the rewards. If you want to go through them in more detail, well, why don't I just show you here maybe 1 or 2 of them. Yeah, so here's the int reward function. It's taking out the responses, and it's checking, it's giving half a point if basically the response extracted is a digit and 0 otherwise. So that's the int reward. And I should say these rewards are designed by Will Brown. Will Brown has a very nice and compact script that you might want to grab. It's on GitHub. Let's see if I can find it. If you go to Will's GitHub and then GRPO Llama 1B, he actually has a single script that you can run here with transformers. It's not unsloth, that will allow you to do the fine tuning. And the rewards he has here, these are the rewards that I'm using. Okay, so that describes how we do GRPO, and that's what I do. So I run the GRPO. Let's see if I can find the script for running it. Okay, so for GRPO, I've actually put the instructions up in the top section. If you go to reinforcement learning and then you go to GRPO training, you'll see here some installs. There are some specific installations that need to be run. So Unsloth and VLLM need to be installed, and you need to install a specific version of TRL. And these are also in the Unsloth collab if you need them. Then I run Python train Unsloth GRPO, and I run it on GSM8K on the training split. So this is pretty much the command here for GSM8K. I have another script I haven't tested entirely for running an ARC. That's a different data set. And when that's done, the model will be saved. And there's an option then, actually, the model will be saved every 50 steps. I can't see that now because I ran it on an older instance, but you have the option then to merge. So merge the LoRa adapters from any one of those steps to create a saved model for any step. And once you have the saved model, you can maybe push it to hub, or you can run inference on it. So what I did was I saved the model. It's actually pushed up on hub if you want to check on Hugging Face. And then I ran inference. I'll just show you the snippet for running inference here. I ran with sampling batch inference, and I did it on the 100-step checkpoint. I'm going to show you the results now in a second. I sampled 8 times, which is what I'm doing for every evaluation, and I ran on the test set. And yeah, this is pretty much how I got the performance. There is this reasoning flag here. Just a small note, it is important. In the first video, I was using think tags. So I would use tags like this, think. Whereas in this video, I use reasoning tags. It shouldn't make any difference to performance, but I used reasoning here just because that's what's used by Unsloth and Will Brown, and I just wanted to run everything in the same way as a check that what I was doing was making sense. So I'm going to show you now the results, and then I'll show you the TensorBoard. And basically what I find for GRPO is that the pass at 8, this is the baseline, but the results after GRPO, it goes down from 79 to 75%, and the majority at 8 goes down from 35 to 30%. So basically with GRPO, the results actually get worse than the baseline. And it's hard to pinpoint exactly why they get worse, but possibly it's because the model is optimizing more for the format than optimizing for getting the answer correct. And we can kind of get a sense for that if we look at the logs. So I can run TensorBoard here. I'm in the RL folder. I'll just run TensorBoard. Let's see if it's installed. It may or may not be. And log dir logs. And it's not installed, so I'll do uv pip install TensorBoard. And now I'll run here. Don't know what those errors are. And the model I want to check is GRPO. So let's take a look at what's happening during the training. So first of all, we can see that the total reward here is increasing over time, which makes sense. And then it's plateauing out of 2. Now the maximum score is 4 because we've got 2 for correctness, and then we've 2, which is a sum of 4 times a half for each of the other rewards. So if you had a perfect model, it should be scoring 4, but you can see it's not. It's kind of plateauing here around 2. By the way, 100 steps is roughly half of the training data. I stopped it at that point because I'd been running for well over an hour and the performance is kind of flatlined, but you could continue to run it out for longer. And that may have some effect on the results, but the fact that it's making the results worse is definitely a bad sign. You don't see that with SFT, even with a smaller number of samples than a total training set. So that's the total reward, but we can zoom in then on some of the specific rewards. So for example, the correctness reward, we can see here, and it does improve, but then it's plateauing after about 50 steps. The integer reward, it's very close to 5, so it's pretty much consistently generating an integer. The soft format reward and the strict format reward, they're kind of asymptoting at 4.4 out of 0.5. So yeah, the model's not completely consistent in format, but it's getting there. And something I should say is that because I provided the one-shot example, I get performance that starts, that rises very quickly. And there's actually a partial run I can just show briefly. This is where I'm not using the one-shot example. And you can see the format reward is just really bad at the start. The strict format reward is very poor. So if you don't do a one-shot, you're going to spend a lot of time in GRPO just kind of wasted, where you're sampling, but you're not hitting an answer that's giving you a dense reward. So it's going to be slow. So the one-shot makes a big difference. And this is a key point with GRPO. There is no dropping of bad samples, or if you have 8 samples generated and they're all bad, which means the group is just collapsing to 1 point and has 0 information, you're still going to backprop on that. And so GRPO can be quite sample inefficient. Now, you could in principle build in some rejection sampling. It probably does make sense to do that into GRPO, but if you run it in naive form, you can just get very slow convergence for these reasons. So yeah, you can see that the format rewards are basically coming up to a pretty high level, but the correctness reward, which by the way has a max value of 2 if it was get everything correct, it's clearly falling well short. It's even well below 1 here. Just some other comments here. The training completion length is falling as we go through training. This is largely because some of the wrong answers just kind of blab on. And initially you see that falling. What I have seen when I do loops of supervised fine-tuning is I do see some kind of slow increases. It'll fall initially as it gets rid of the bad answers that are long, and then it kind of, I maybe see some evidence of increasing in completion length then, which by the way is what DeepSeek sees. So if you look at the DeepSeek or1 paper, and if you scroll down to the graph here, and this is a large number of steps, probably with a large batch size, you can see that the reasoning lengths are increasing very significantly over time. Now, this also could be due to the model doing some backtracking type behavior that becomes stronger in larger models, and I'll make a video about that in future. But anyway, this is kind of what we'd expect if we perfectly replicated DeepSeek, albeit this is on a much larger model. And I'm just saying that if you look initially at your results, you see the opposite. The responses get shorter, but this actually makes sense because we're just kind of getting rid of these long, verbose, wrong answers. And potentially at some point it might go up again. But we are kind of plateauing in terms of reward. So it's not obvious we're making a ton of progress here. Just some other comments. The grad norm it's kind of okay. Maybe some of these spikes are not ideal. I like to see it down towards 1 and less. And here's the KL divergence. So this is trying to pull the model back to its base. And notice how the KL divergence is actually increasing over time and then kind of staying steady. And the loss consequently, because the KL divergence is going up, the loss is going up as well, kind of matching this. KL divergence is being used to penalize the model. And the reason why the KL divergence going up is kind of a problem is because, well, it's good and bad. It's pulling the model back to its base, but it may also be blocking the model from finding some better optima that would lead to better performance. So this is pretty much the performance of GRPO. And I've covered all the techniques. So I think we can move now to cover the graphs here. And we can look first of all at the summary, which is the majority at 8 graph. And you can see the baseline. You can see supervised fine-tuning improves. ORPO improves as well, but not as much. And you can see GRPO disimproves. Now, you can run multiple iterations, so you can run SFT again, and I did that, but I didn't get a significant improvement. You can also run a first round of SFT, get that model, generate ORPO pairs, and then run ORPO on top of that model from the first phase. And yeah, I mean, this is all probably within error, so I'm not finding at this model size that I'm easily able to recursively improve performance. And SFT2 here is where I take a data set generated with the first SFT1 model and I train the base model. So whereas SFT1, SFT2 means I'm training a model that's already been trained for one round with better data, here I'm just taking the better data and training the original model. And here again, it's probably just within error distance, so it's not clear that it's improving. Now, you could argue there are hyperparameter optimizations that need to be run. I did do some hyperparameter optimization. I tested out different learning rates, and this is kind of the best I could get with SFT and ORPO. But you can always argue there's more hyperparameter optimization to do. Now, here's the pass-it K. And notice that I'm not a huge fan of doing this, so I criticize myself, but the y-axis starts at 70 here, so it's not a big range. Basically, the baseline and SFT1, there's not a whole lot of difference, maybe a small improvement. Doing a second round of SFT seems to keep the model also within a similar range. Doing a second round with ORPO seems to make it worse here on pass at 8, and doing just a first round of ORPO seems to make the pass at 8 worse. Doing SFT with a better data set also seems not to improve the pass at 8 much, and doing GRPO reduces the performance of the data set. So in sum, by using reinforcement techniques, and I cover all of these within reinforcement learning, we're able to get improvements in the majority at 8. So we're able to get better consistency in how the model answers, but we're not easily able to reach new answers. Now, there could be a few reasons for this. A most basic reason is that the model is not pre-trained on enough maths data, so there aren't underlying patterns there that we can elicit through the reinforcement learning. Possibly the model doesn't even have enough parameters to capture the pre-training patterns that are needed to do maths. And for this reason, maybe you would see behaviors at much larger sizes and with much more pre-training data on a model like DeepSeek or ORPO, for example. Now, I should say probably they both have similar amounts of pre-training data, but that's complicated by the fact that the Llama 1B model is actually distilled from the larger models. So it actually doesn't have the same volume of training data exactly necessarily. And the distillation also confuses things because it means we're embedding knowledge here from stronger models that probably would be very hard to reach just by using ORL on the weaker model alone. So this kind of sums up what you can do in terms of performance with SFT and GRPO. But I want to make this more applied in general so you can use it if you're thinking about your own data sets. So let me talk a bit more generally about the performance that you can get and how I recommend doing reinforcement learning if you're looking at a custom application. Now, before I go into a flow diagram to help explain when you should do SFT, reinforcement learning, or how you should do it, I just want to recap on what I see as the difference between GRPO versus rejection sampling and SFT. So these are the two main methods I looked at. And the difference, I would say, is in the backpropagation. So in supervised fine-tuning, the backpropagation is based on simple cross-entropy, which increases the chances of good answers, whereas in GRPO, it does a few things. GRPO will shift the probabilities and it uses KL divergence. And when I say shift probabilities, it will increase good answers and decrease bad answers. So it's not just increasing good answers. Now, a different way you could say this is it has the ability to provide a negative reward. So whereas with supervised fine-tuning, you're just providing positive rewards effectively for the correct or the most likely next token, everything else is getting a 0 in terms of the probabilities you're trying to target. With GRPO and with ORPO, you've got the ability to do positive reward and negative reward. So in theory, this is good because you can move away from bad answers and towards good answers. In practice, though, it's not necessarily obvious that things will always work out that way, because when you reward a good answer, by definition, probabilities have to add to 1. You're always going to be softly reducing all of the other outcomes. So there is a way that in practice, just by doing the cross-entropy, you could actually achieve a lot of the effects of encouraging the good answers and eventually with enough data discouraging the bad answers as a consequence as well. I think one of the misconceptions around GRPO is that it's maybe unique because you can provide custom or continuous rewards. But actually, if you can design any specific reward function, you can, I believe, make that into an equivalent sampling strategy. So if you ask a question, let's say, what is the capital of France? And you generate 8 answers, some of them are right, some of them are wrong. You can define a correctness function, a correctness reward function for the one that says Paris. But equally, you can define a filtering rule that says, let's drop that from the data set we want to use for supervised fine-tuning. And if you have kind of a more soft reward function, let's say the soft reward function is you're going to allow any European capitals and give it half a point. Well, in that case, you can define your reward function, gives half a point for soft capitals or for European capitals. But you can also define a rejection sampling approach where you will reject maybe 50% of the answers if they have European capitals in them, but you will keep 50%. And you can, of course, target different proportions of the data set to have certain characteristics. So basically what I'm saying is, yes, it's nice that you can tailor reward functions in GRPO, but it's also true that you can tailor rejection sampling, and you can do that on a continuous basis in principle as well. So I think largely these are equivalent. I'm probably missing some specific nuance points around where there might be some benefits, but broadly speaking, the difference between GRPO and ORPO and DPO and SFT with rejection sampling, or ORPO with rejection sampling, the difference is really around the backpropagation. And the key big question is, in practice, does the ability to do negative rewards actually help? Or in practice, do you just end up more or less performing like doing cross-entropy loss? Okay, so with that rather theoretical note, let's look at how to do RL. And I'm going to say RL to cover rejection sampling, supervised fine-tuning, or GRPO actually is what I meant to say here. You could use SFT or ORPO as well, either. But I'm just trying to be generic in saying RL. And the starting point is up here. Let's say you have a custom application. The first question you ask is, when I want to fine-tune a model for this, is there a stronger model like R1 available that can create good answers? Because if there is, I would argue you should use that strong reasoning model to create long chain of thought answers and do rejection sampling on those answers and do supervised fine-tuning. Now, if R1, or the strongest permissible model, is not giving you good answers on your application, now you have to ask, well, do I have a small model that's pre-trained on data, and that data is well encoded, which I know is somewhat subjective. Well, you should make it objective via an evaluation data set. But do I have a small model that's pre-trained on the application? If you do not have a small model that is pre-trained on the application, then it's probably going to struggle to improve with reinforcement learning. So you need to find some data and you need to pre-train that model. And by the way, if that model is too small, maybe you're not going to be able to ingrain that data with enough granularity. And so you might need to move to a bigger model. So let's assume now, okay, DeepSeek R1 is not good enough to generate synthetic data. I've got to do my own model. I've found a data set. I've pre-trained a model that's big enough to represent that data set well. And by the way, that's not a trivial thing to measure, but let's assume you do that. So you now have a model that's well pre-trained. Now you need to ask, do I have question-answer pairs or can I write a verifier? Because these are the things you're going to need if you want to do rejection sampling or if you want to do GRPO. And if you don't, you'll have to figure out a way to get these, either generate them through human methods or synthetic methods. And once you have the QA pairs and or can write a verifier, by the way, if you have QA pairs, you can always use those with a judge in order to build a verifier. That's effectively a verifier. Or maybe you have a verifier like it's a code execution environment where you check the answers. So assuming you have this now, you can move to RL. And in RL, whether you do GRPO or RS, rejection sampling, supervised fine-tuning, you can start by crafting rewards or filters, which I've argued are somewhat equivalent. Then you sample, then you backpropagate, and then you repeat this process again, sampling and backpropagating, and then refining your rewards or filters to try and get the performance that you need. So this is kind of the flow I recommend. Now, to decide between whether you want to do GRPO or you want to do rejection sampling in SFT, I propose the following list of pros and cons. So the pros of GRPO, the first is that it's somewhat easy to use because it's packaged in a single library within Onslaught. Now, Onslaught just supports one GPU. If you want to do multi-GPU, maybe you can use GRPO from Transformers, but it's not going to be particularly memory efficient, so you'd have to find some other library. Another pro of GRPO, backprop may be more targeted than SFT because it provides these negative rewards like ORPO, so maybe that's a benefit. KL divergence may stabilize your training, so your reinforcement learning might not diverge quite as far. Now, granted, you can also stabilize in SFT by blending in some pre-training data or some instruction data that's more broad than the data set you're trying to train on. So there are different ways to stabilize, but GRPO does provide KL divergence in order to achieve this. Now, cons of GRPO. KL divergence may stop the model from reaching global minimum, so it might actually hinder your progress. Note that it's not standard to use KL divergence in pre-training or in post-training when you're doing supervised fine-tuning. So clearly, we're able to make a lot of progress without KL divergence. So it's not necessarily obvious KL divergence always helps. It could hinder you. Reward hacking is a big problem in GRPO because you're adding together, not just you're adding together rewards, which means it might optimize for one over the other, but also you could just have reward hacking even if you have one reward. Co-optimization of rewards may lead to local minimum. That's actually just what I said. Because you're putting in these multiple rewards, you might see the format gets very good like we did in this example, but actually the correctness kind of plateaus. Another issue with GRPO, the library may not use the fastest inference. So I've used SGLang when I did the iterative SFT with the rejection sampling, but the Onslaught implementation uses VLLM, which I think is slower for larger batch sizes. And then the last point here, GRPO doesn't drop overrepresented samples. So GRPO is quite sample inefficient. Unless you build into GRPO to drop samples or groups of samples where there's little information or diversity, then you're going to be backpropagating needlessly and just wasting compute. Now, this is an improvement you can make, but in the naive form, GRPO is going to be inefficient for this reason here. Okay, so that rounds up this comparison of SFT versus GRPO. I realize I'm making a fairly forceful case here that in a lot of examples, just doing SFT is going to be more robust and possibly even better than some of the more complicated techniques. And I do like the idea that simpler things are better. That being said, GRPO and ORPO does have the ability to do the negative rewards. And potentially there are some practical ways in which I'm just overlooking how GRPO could be helpful. Maybe if you scale to larger models or to larger infrastructure, just practical things that I wouldn't be able to appreciate by running these smaller models at the scale that I am. So let me know any questions. I'll put some links to parts 1 and 2 in the description. And if you want to get the materials, they're available at trellis.com/advanced fine tuning if you want to purchase the annual or lifetime membership. Cheers, folks.